All right. Hopefully you can hear me. No one's here, so I'm just gonna get started because I have a lot to get through. I'm just gonna like go through some problems, hopefully four in this hour. Um, so yeah. So the first problem we're gonna be doing is 321 from chapter 4.7. It's a pretty simple optimization problem, but honestly, optimization, you can kind of just compare any kind of optimization problem to all the other ones. It's the same thought process, just with different shapes and different sort of setups. So our problem is going to be we're constructing a fence, construct, wow, construct a fence around area of 1,600 feet squared. Dimensions of sides to minimize what is it? Minimize amount of material needed. So the first thing we want to do is consider like the shape that we're working with. So clearly, of the rectangle. So it specifies rectangular pen. Rectangular. Right. Cool. So it specifies that we have a rectangular pen. Hey Miles, how's it going?
Hey.
Can you hear me okay?
Yeah. Yes, again.
Oh shoot. Can you say that again?
Yeah, I can hear you.
Cool. I can hear you as well. Okay, I was just going. Can you like see this? Okay, I don't know if like the lighting is kind of bad. Like the paper.
No, yeah, I can see it.
So I was just gonna go through some problems today, covering like some of like the more difficult sort of topics. The first one we're gonna be working on is optimization. Then we're gonna be doing like a L'Hopital, a linear approximation, and then hopefully doing an asymptotes one. So finding asymptotes and like doing like limits at infinity, stuff like that. So I was just setting up this problem, working with, I mean, I kind of have written it out here. It's problem 321 in chapter 4.7 in the online textbook. I don't know if you've done it or if you've seen it. That's what we're going off of. So basically the setup is we're constructing a fence around an area. It's a rectangular fence around an area of 1,600 feet. We want the dimensions of the sides to minimize the amount of material needed. So typically when we look at an optimization problem, we're dealing with some kind of shape, and then either dealing with the volume of it, the area of it, or the perimeter of it, almost always. Unless we're not really like dealing with the shape and it's more like hypothetical in question, but I am pretty confident in saying that they're not going to see a problem that's optimization. It won't be a shape on any kind of like test or anything. So right now we want to consider, I mean, as we can kind of tell, okay, this is going to be dealing with some kind of shape thing. We want to think about, okay, what shapes might we, what like aspects of a rectangle might we want to be working with? So we have volume, area, perimeter. Now, we know we're going to be working with area because it literally specifies it in the problem, right? Volume, it says nothing about the volume, so we probably don't want to do that. And then we're talking about the amount of material needed. So material would be like, okay, how much actual fencing will we need to create the fence? And so that specifically refers to the perimeter of the fence, right? Does that make sense? So we kind of like can figure out that we need these two, right? Okay. So the next thing we would want to do is to set up this area and perimeter sort of like as equations, right? Or as formulas. But whatever we can plug in from our problem, we will want to actually like plug in into those equations, right? So we know that the area of a rectangle is like base times height, right? Okay, but we don't really know what these are, what the base and height are, right? Because that's what we're trying to find. Area, however, we do know what we're working with, right? Because it's given to us in the problem. It's 1,600 feet squared. So we can sort of like move this over to 1,600 equals BH. Okay, cool. Or actually, I'm going to change this to X and Y just to like make it easier to work with. Same thing though. I guess we can like draw some things, 100. Typically when you're, actually that's poor. Typically when you're dealing with any kind of shape problem, I strongly recommend drawing it out. Drawing it out just makes it a lot easier to sort of like visualize and sort of like work with in your head. Literally always like just draw a picture. It'll make everything easier. Okay, so now we have the area, cool. Now we need the perimeter, right? So perimeter is just like, okay, x plus y plus y. So that would be like 2x plus 2y. Okay. Awesome. And then we can sort of like change this to be like 2x plus y, right? Neat. Actually, I want to keep it as just this. Sorry. Okay. And so now the next step generally when we're sort of working with these optimization problems is looking at these two equations and figuring out a way to use them together to then work with like the type of sort of like the aspect of one of these three variables that's left over that is relevant to what we're trying to like find out, if that makes sense. So we're trying to minimize the amount of material needed. So that means that we want some kind of equation to model how the perimeter is changing as we change some variable, right? So theoretically, we could honestly like change, we could, well, to do so, we need to get rid of one of these variables. We need to get rid of x or we need to get rid of y, right? Because we can't really like differentiate at all to like find rates of change and stuff with both of these variables still in here. And so to do that, we're going to use our constraint equation, which is the equation that you plug a given value into in the beginning of like when you're working out a problem and stuff. You want to solve for x, you want to solve for y, and then plug that into your other equation, which has like the property, or like sort of like I don't know what to call it. Just like the variable. I hate to say that, but yeah, var to work with. It's more like var to investigate, right? Does that make sense? So in this in these optimization problems, you could be given like the volume of some kind of like box. And in that case, you know, you'd have you would do like v equals x, y, z, right? And then you plug in for volume, and you'd probably be given like, you know, something like it's like a box, and then this is x, this is x, this is y. I think we did this in class. And then it, instead of having three variables here, you just have like x squared y or something. And then you plug in for v for like some number, and then you could solve for y pretty easily. And then you plug that in. So it's always about like, okay, set up two equations. One of them is the constraint. The other one is what I'm going to be doing derivatives and stuff with every single time. Does that make sense? Cool. Okay, so I'm going to solve for y here, which is pretty simple. I just divide, right? Okay. And then from there, I know that whatever y is here, it's going to be equal to 1,600 over x, according to our constraint. So I can just plug that in. Okay. And now all I have to do is just sort of like simplify. Oh, shit. Awesome. Okay, so now I have some function that looks like something that tells me, okay, as I change this value x, as I shift it along, my perimeter is also going to change, right? And we're trying to find the lowest perimeter possible because this that y value that we originally had is sort of like bounded to or constrained by that original area that we sort of used to then like switch the variables around with and stuff, right? So now on this function that we have here, it's gonna look like some kind of like you can't really see what I'm doing. It's gonna look like that. It's gonna have its local mins and maxes. We want to find some local minimums, because we're trying to minimize the amount of materials needed. So how are we gonna find local minimums of this function?
Do you have to find like the first derivative?
Yeah. So after we find the first derivative, do you know what like sort of is the next step after that?
Then you like find where it's increasing and decreasing, and then use that to find like the max and mins.
Yeah. So, well, let's start with just finding the first derivative first, right? Okay, so let's do p. So what's the derivative of 2x? 2. Okay, you can sort of get that. This is also like 3200 x to the negative first. So if I just quickly minus 30 so second equals. Does that make sense? Does this all look good? Yeah, cool. So now what we want to do is we have this derivative function that sort of tells us where the original function that we have right here is increasing, where it's increasing, and then also where it's decreasing, right? And so wherever this function is positive, we know that this function, this original one that we were sort of working with, will be increasing, yeah? And then wherever this derivative function is negative, then we know that original function is decreasing, right? And so that becomes the whole thing where like, okay, if we sort of go between being positive and being negative in this derivative function, so like positive to negative, that means that we're increasing into then decreasing, right? And so what that looks like is that local max. And then when we are going from negative to positive, or down, over, and up, that's our local min. So we're looking for a time when, as we're going from right to left for x values, we're looking for that negative to positive. Okay, so how do we find out where it's going from negative to positive? Well, we just solve for 0 because that's where it's going to be changing, going from sort of like the negative side to the positive side on the y-axis, right? So we just set it equal to 0. 2 minus 3200 over x squared. Couple of different ways you can go about solving this. I'm just going to sort of like do it kind of quickly. I'm going to, yeah.
Can you also use like the second derivative test?
Let me see.
Because like if the second derivative is positive, then, or wait, yeah, if it's positive, then it has a local min, right?
Second derivative is positive where? Just like always? Or
Like for the second derivative test, I wrote down that if the second derivative at like a critical point is positive, then f of x has a local minimum at that critical point.
oh, okay. Yeah, so that could also totally work, and I can show you that in a second as well. I can definitely show you that in a second as well. Sorry, I'm just like looking. Cubed. Okay. Yeah. So do you find that critical point? Where do you find that critical point from? Do you think? Do we find it from the first derivative, or do you find it from the second?
I think that you can find it either way.
Okay.
I don't really remember though.
Okay. Yeah, so I mean that is a totally perfectly like acceptable way to go about doing this, 100%. That's not really how like I've trained myself to go about doing these problems, but yeah, I think that if you take second derivative and if it's like always, yeah, I think what you said makes sense. I mean, if you have it in your notes very explicitly and you have like an example of that happening, and if that's more comfortable to you, then like feel free to go about like doing it that way. But again, that also would sort of like include, taking another derivative in addition to taking this first one. So it's sort of up to you on how you would like to do that, if that makes sense. Okay, yeah, cool. So do you want me to just sort of finish out this problem in this direction? That's all right, cool. So I'm just gonna solve for x now. 3,200 over x squared equals 2. We can divide each side by 2 to get 1,600 over x squared equals 1. I can multiply the x squared over to get 1,600 equals x squared, and then take the square root of both sides to get x equals 40. Technically, it would be plus or minus 40, but then we can't really have minus area or minus direction, so that's not, or minus length, I guess. So that's not really possible. Okay, so what is finding x equals 40 tell me, like with regards to the rest of the problem?
Wait, sorry, could you just repeat that?
Yeah, what is x equals 40? Like, what does 40 mean for here? For this problem?
It's one of the side lengths, right?
Yeah, exactly. So x equals 40 means that we know that one of the side lengths is gonna be 40. Technically, what we could do is plug this back in to our well, we could make our whole like number line thing, right? At 40, and make sure that we go from minus, excuse me, from negative to positive over time, and you can sort of like plug in. Okay, let's see. We plug in 10 here for this. If we plug in 10 here, that's 100. 2 minus 32 over, or 3,200 over 100. So that's 32. 2 minus 32 is negative 30. You see how I've done that? And so that means that like, okay, anything on the left of plugging 40 into the derivative is going to be negative. If I plug in like 3,200, I guess, which is on the right side, that would be 2 minus 1, and that's going to be positive. So that makes sense. So we have this whole, it's like, boop, because decreasing into increasing. Cool. So then now all we have to do is plug our x value back into our constraint equation. We sort of have done all of the hard work, and now all we have left is just go back to where we started and then solve for that final value. So we started with 1,600, awful 6, equals xy, or I guess it's 40y now. And then we divide and we get 40. So that means x equals 40 feet, y equals 40 feet. So it ends up just being a square area, I guess, square pen. So yeah, so that's sort of like the general direction that you should take when you're sort of approaching linear optimization problems. In the textbook, there is like a little bit down from the top of 4.7. It says problem solving strategy, solving optimization problems. I strongly recommend you go check out that little box and then just follow, okay, like where is number 1 on this problem that I just solved, right? So you can look at all the work that I've done, find out where number 1 is, and then sort of correlate that to see an example of it. And then look for number 2, see, okay, what part of this page or whatever page you've written out, correlates to number 2. Same thing with the rest of them. That way you can just really see the step-by-step process of how to solve one of these. Every single one follows the same process, every single one. It's just important that you sort of like understand that process and know how to apply it to different situations. if that makes sense. So yeah, cool. Okay, so I have a couple of problems sort of laid out for us. Are you interested in doing like a L'Hopital or a linear approximation, or finding an asymptotes one? Any of those are good with me.
Yeah, I wrote down both of those as like things that I wanted to ask you about, so that's actually perfect.
Which one specifically do you mean?
Wait, so hold on. I need to change my.
We could do the L'Hopital problem or linear approximation or finding asymptotes.
I guess linear approximation.
Okay, cool. I'm just gonna put my water over here. Okay, so the first thing to know about linear approximations is that you're basically finding values to plug into a formula. That's you need to remember. So that formula that I'm talking about is this one right up here. Is this L of x equals f of a plus the derivative of f of a times x minus a. So that's basically what you're solving for, right? You're basically plugging in, you're basically doing stuff given this sort of value, and finding some way to plug stuff into here to then get again like some value out. If that makes any sense. Sorry, that was like poorly explained. So the first thing I sort of think about when I look at a problem like this, where okay, I obviously don't know what the square root of 8.99 is, but what I do know is that the square root of 8.99 is basically just plugging in 8.99 for x for like the function just the square root of x, right? Does that make sense? So you can sort of model this equation as this being f of x equals square root of x with, sorry, it's a terrible W, with x equals 8.99, right? Okay. And so this is actually where we get that idea of f of a and f prime of a, right? So this sort of equation that we found is exactly what we're going to be using to find these values. However, now the problem is like, okay, there's also this a value here. Like, what do I do with a? Right? So are you sure are you at all like sort of sure what a might be, or how we might what we might plug into that to sort of get a good estimate of what sort of like the square root of 8.99 is?
I'm just confused on like how to find it. It's either like is it 0.01
So
or is it like 9? I can't
9.
tell.
Yeah, it's 9. So
Okay.
we use 9 because that is not only very, very close to this x value of 8.99, but we can also find what f of a is, right? If we use that as our a value. Does that make sense? So there's sort of two criteria when choosing an a value. The first one, is it close to this x? Is it close to that? The second one is, can we plug it in to our new equation that we've sort of created using our original expression, and can we just solve it simply, right? So if we use a equals 9, we can pretty easily do f of a, right? Equals 3. Yeah, I guess plus or minus 3, but we're just gonna work with 3. So those are the two criteria. Close to x. Close to x. F of a is easy. Yeah? Okay. So if I wanted to set this problem up, finding ln of 0.99. What would I use as a here?
One.
Yeah, exactly. Because 1 is close to 0.99 and ln of 1 is just 0. So we know how to find that pretty easily, right? And we could do that for a bunch of different things. Like, I mean, I could, like, the list could go on. Like, you could do like sine of, I guess, okay, I want to stop using 0.99, but like 0.99, or no, that's a bad idea. Oh, sine of, oh wait, no, sorry, shit, I keep, okay. What about like cosine of like 3.14? What would you use for a there?
Pi.
Yeah, right, because again, like pi is very, very close to 3.14, and we know that cosine of pi is -1. So those are some examples. Cool. Okay, so now that we have our x, so we have our x value, right? So we know we have x. Great. We have our a value. Awesome. And we have our f of x function. Cool. So now all that's left is to basically use a alongside f of x and find out what these values are, right? So we already found f of a, so we're kind of good here. We found x, we good. We found a, cool. So now all that's left is f prime of a. So how do you want to go out finding that?
Well, you just turn 9 into, or the square root of 9 into 9 to the half power, right?
So doing 9 to the half power, I mean, it's basically the same thing because doing like 9 into this, whenever you write like sort of exponent like this, it basically it's the same thing as saying you have a square root there of like.
Yeah, I just meant it'd be easier to find the derivative if you like put it in that form.
Yeah, 100%. So yeah, we're looking to do the derivative, right? So instead of doing square root of 9, I'm going to do square root of x, right? Just to keep it so that it's like an x. So we can do f of x equals x to 1/2. Yeah. And then I just take the derivative of this, right? To get it into that f prime. Cool. F prime of x. It's a pretty simple derivative. Just 1/2 x to the -1/2, right? Cool. You can sort of like write this out again. So what is it? It's like 1/2 x to the 1/2 was 1/2 square root of x. So I simplified that. Yeah, cool. And now again, we just need f of a, and we know what a is. So f prime of a, rather. Plugging in 9, and now we just solve for this. Oh shit. 2 times 3 equals 1/6. I'm really bad at drawing sixes. Okay. Cool. So is 1/6 what you got too? Awesome. So now we have f prime of a, and from there we can solve. So all we have to really do is just plug all our values in, and that's our linear approximation. I'm going to plug in x on the left side as well for L of x. Our x value is 8.99. So f of a is 3 plus f prime of a is 1/6. X is 8.99 minus a is 9. Then you just do some pretty much just like arithmetic. Oh shit. 0.01. 3 plus 1, 6. This is negative. Sorry. Does this line sort of make sense? Yeah. Yeah, I mean, I feel like it would be a little bit harder to do like 1/6 of that, so I just turned it into a fraction instead. Just a little trick, I guess. So yeah, I mean, this is our answer pretty much. If you want to plug in square root of, actually, I can just do it. All right. So 1799 divided by 600. Okay, we got some 2.99 number. Okay. Sorry, I gotta like turn my phone. Oh, jeez. All right. And then we do 8.99. Oh my God. Square root of that is pretty close. So yeah, kind of is a good approximation, right? So this is sort of, again, the general path that you'll take when doing a linear approximation problem. And they can be shown in different ways, but they almost all reduce down to, okay, finding an f of x, finding an a value, and just plugging stuff into this formula, right? And you'll have your notes, so it's not like you'll forget this, right? So I think you should be okay. It's not too bad. It really just involves one derivative and plugging stuff in. So yeah, does that sort of clear things up? Cool. Do you have any questions about the things that I've like gone over so far? I feel like I don't ask enough. Okay, cool, great, that's good. Okay, so are we thinking L'Hopital or asymptotes? I feel like L'Hopital is like not too bad, but if you want me to go over it.
Yeah. Maybe I think L'Hopital is fine. So yeah, maybe just do the asymptote.
Sounds good. So this asymptotes problem is a bit longer than sort of other ones, just because not only do you have to find vertical asymptotes, but you also have to find horizontal asymptotes. So to sort of just go over again, like where we know vertical and horizontal asymptotes are, I sort of made this little box in the top. I don't know if you can like see it too well. I can like zoom in. Sorry. Okay. All right, there we go. We can really see it now. So is it like focused at all? Wait, I'm gonna like focus it. Okay. So right here, we have our inputs, these two. So right here, we have like just plugging in some value A, some normal constant A. And here we have infinity. So, and by that, I mean like when you're taking the limit of some function, that's what I'm talking about. So this is for like lim as x approaches like these things. That makes sense? And like f of x equals, and then like these things. Yeah. That's how I sort of like set up my box. So if I plug in some constant a and I get out a constant c, what does that tell me? Well, that's basically just as if we sort of did some, limit as x approaches a, f of x equals c, and that's basically just the same as, I don't know, yada yada, plug it, we go to a, this is c, and basically all that it tells us is that, okay, like it's like continuous here, there's a value at f of a, or there's a removal of discontinuity, right? So plugging in some constant and then getting out some other constant, not really the same. I think this actually might be an L, sorry. So that's something to like sort of take into consideration. If you plug in the limit of some constant and get out another constant, doesn't mean anything. So what if you get out an infinity sign? Well, that would be sort of the case where you're going like this. Oh, right? This is A. So you just plugged in your limit. It's a one-sided limit, unfortunately, but it would be a one-sided limit. and you're never going to touch this a value, right? It's always going to go up to infinity. In that case, we're working with a vertical asymptote right here, right? Okay. So that's sort of like the two cases where you plug in x, where you're taking a limit to some normal value like a, which I'll show you in a second. The other case is if you take a limit to where x goes to infinity. So that means like all the way to the right of some function or all the way to the left of some function. If you get out a normal value, you're going to have a horizontal asymptote, right? Because that's the case where you might do it like this, and then you're like, oh, you're never going to hit it. That's L. So you're never going to hit this L. So you're going to approach L as you go to infinity, but never actually touch it. So that's one of the cases for like a horizontal asymptote, or it's the case for a horizontal asymptote where you plug in infinity for your limit and then you get out a constant. The other case, though, is where you plug in infinity. Sorry, I'm not showing you the box. The other case is where you're plugging in infinity and you get out infinity. And this is just, almost any normal function that we've seen before. It's it's linear, it's our quadratic, it's cubic. All of these functions, you plug in an infinite limit to infinity and you get out an infinity sign, right? Because like limit as x approaches infinity of x is just like infinity, right? That makes sense? Yeah. So what we want, looking for, sorry, okay, I'm going to zoom back out. Sorry, that's like really hard to like watch me do. Okay. What we want, lim x goes to a, f of x equals infinity, plus or minus infinity. And this can be from either side. Or lim x goes to plus or minus infinity and goes to some number L. Yeah. So that's what we're looking for. Cool. And we have our function already up here. So we don't need to do any derivatives. We don't need to do any fancy stuff like that. We just need to basically be smart about how we plug stuff in. Okay. So I know I've taken up a lot of like space on here, but we're gonna sort of like try to figure everything out while we've got time. So which one do you want to start with? What do you want to start with?
It doesn't matter to me.
Okay. Do you have like an idea of like where you might start for finding the vertical asymptotes, for example?
You would have to find A, right?
So yeah, you need to find A. Exactly. Yeah, exactly.
I just don't remember how to find A.
Yeah, for sure. That's totally okay. Like literally don't worry about it. So the A's that we're going to be looking at are wherever we know that f of x is not defined for. Does that make sense? And we know that f of x is not defined for some values because we have this fraction here. So whenever the bottom of this fraction, the denominator of this fraction is 0, then we're going to be dividing some top number by 0, and we can't have that. So first things first is to figure out where this bottom part is equal to 0. So we can start writing that out. I don't know if you've like gotten past this part. Did you do that? Yeah, that's what I was assuming you were doing. Cool. So what does this mean? Well, if we plug in 5 here, that's going to be 0. this is all gonna be 0, right? Or if we plug in 1 here, it's also gonna be 0. So you can say that when x equals 5, x equals 1, well, this is gonna be 0. Equals 0. Sorry, that's really poor notation, but you know what I'm saying. Cool. So those are our two like possible places where we may have asymptotes. Yeah. So one check lim for lim x a for a equals 5 1. Okay. So how do you want to go about doing this?
I mean, you just plug each of them into like the limit, right? And then use f of x.
Yeah. Yeah.
But don't you have to like factor both parts or whatever and then cross off?
Yeah. Exactly. You got it right. Totally. So we can sort of rewrite f of x up here, right? Which you probably noticed. So we can sort of rewrite f of x. I'm just going to do it directly. So I can factor out this x, right? So x, that's going to be x minus 1. And then we already factored down here. So I can just take that. And you'll probably notice we canceled. Cool. Cool. So working with this, what was I going to say?
5 wouldn't work then anymore, right?
Yeah. So 5 doesn't work anymore. And so what that tells you is that you need to look into 5 a bit more, right? Because what the limit, if the limit of x approaches 5, x over x minus 5 doesn't exist, D and E, right? That means that it's sort of looking like it's not going to the same place. So it's gonna go in like this, or it's going like this, or it's going like this, right? So it's not ending up at the same place. And so what that means, rather than it doing this and just having a removable discontinuity. Yeah. Whereas if you plug in 1 for this, if you plug in do the limit of x approaches, sorry, you can't, can you see? Yeah. If you plug in the limit of x approaches 1, you'll just get jeez, getting out of myself. You just get negative 1/4, right? And so you'll have that removable discontinuity here. Excuse me, because you can't actually plug in 1 into this function. It gets something out of it, but the limit exists. So you know that there's that removable discontinuity. Whereas for 5, you can't plug it in, you cannot plug it in, and the limit doesn't exist. Therefore, we know that there's some kind of asymptote there, right? Does that make sense? Cool. So let's investigate on this page. Sorry, I need to like go to a new page and stuff. So we're looking into the limit as x approaches 5, x over x minus 5. Okay. So when we get a function where we know it doesn't exist, like the limit doesn't exist, that means we need to investigate it a little bit further and go to one-sided limits instead of just sticking with just like two-sided, right? Because as we sort of showed from before, if we find the one-sided limits of all these, we can figure out sort of its it's sort of how it's looking, I guess. How the graph's looking. So you can just do so yeah, if you want to sort of like try to work through these two one-sided limits on your own, that's totally great. You see how I got that? Cool.
Yeah, I got the same thing.
Awesome, awesome. Do you still have sort of like doing this like fake notation? Yeah, it's just like the easiest way for me to think about it. And then if I do up here, uh, we get 0.999. These are miserable numbers. I'm so sorry. We get negative 50. Yeah. Awesome. So that kind of tells us our answer. We have our two asymptotes, vertical asymptotes. And these are our two limit statements kind of proving it. If as you approach 5 of f of x for f of x, as you approach x equals 5 of f of x as if x equals 5, sorry, that's like from the right, I mean, sorry. Then you approach negative, you approach positive infinity, whereas if you approach 5 from the left, you can approach negative infinity. So to sort of like draw it out really small right here, it's kind of like something like this. I think we don't know that there's like horizontal asymptotes yet, but yeah, we're getting there. Does that sort of clear up vertical asymptotes for you? Awesome.
So would
What'd you say?
x equals 1, would that not be a vertical asymptote?
No. And the reason for that
Okay.
is because when we plugged it in, we got a number out of it, right? And
Right. Okay. Yeah. I remember now. Thanks.
box, you plug A in, get a number out, doesn't mean anything. Well, actually, what it
Yeah.
means is there's a removable discontinuity there. Yeah. So, cool. So now we got to find the horizontal asymptotes. How do you want to go about doing this? So we got x again. Um,
Instead of like a or like finding a or whatever, then you would just do like as x approaches infinity.
yeah, exactly. So you can do x squared. Do you follow this?
Not really.
Yeah, so I think
Sort of.
way than that's what taught you guys. But it's basically it's kind of similar. Instead of just dividing by so how I like to solve these limits is I look at the top, I look at the, like the biggest two terms of the top and bottom, right? That's sort of what's important. That makes sense. And then I like to factor those out of the top and bottom individually, and then write them over here so that they cancel out, right? Because x squared and x squared cancel. Yeah. And then everywhere else, you also have to factor those out. So if you factor out x squared out of x squared, you're just going to be left with 1, right? And if you factor out x squared from a negative x, you're going to be left with a 1 over x. Yeah. And it's the same thing with the bottom. So you factor out x squared from x squared, you just get a 1. Factor out an x squared from negative 6x, you'll be left with a negative 6 over x. And then you factor out an x squared from 5, you're left with a 5 over x squared.
Would that process change if like the degree on the top and the bottom were different?
So if the degree on the top and the bottom were different, what I would do is I would still factor out the most out of the top and then the most out of the bottom. Okay. So if this was like 3 or something, then I'd factor out a 3. Yeah. And then here I'd be left with a 1 over x. Here I'd get with the x squared, right? But then, you know, if you go to infinity, all of these go to 0, right? And that's kind of like the main idea is that when you factor all of these things out, this goes to 0 because 1 over a huge number is 0. This goes to 0, this goes to 0. And then all you're left with is like 1 minus a bunch of zeros. Yeah. And so if you pull this x cubed out instead of x squared, then what you're left with is, okay, it's a 0 minus a 0 on the top, and then a 1 minus a bunch of zeros on the bottom, right? And from there, this basically just becomes x cubed over x squared, right? Because this is just 0. So you can kind of get rid of that. And then that just becomes limit as x goes to infinity of x. And that just is infinity. So, and you can kind of tell that like, okay, this top part is going to dominate the bottom part. And that's kind of how you have to think of it. Does that make sense? Cool.
Yeah, that makes sense.
This bottom part, well, and yeah, if this bottom part was what was dominated, then you'd factor out an x cubed out of the bottom, and it would still be 0. Well, this would probably maybe be like 1 or something, but it wouldn't really matter. Well, I guess if that's 0, then you'd be left with, you know, I'm trying to think. It's x squared. This is a bad example because then you're left with this like infinity times 0 thing, right? And so what you do is that's an indeterminate form, remember? So you have to like rewrite it, figure out some L'Hopital bullshit, and sort of, you know. So this is like a poor example. But if they were different on the top and bottom, and like this didn't, oh wait, no, this would literally be still 1. I'm so dumb. I'm so sorry. This is still 1, so it's all good. So we're all fine. My bad. Because you're factoring an x cubed out of an x cubed, so that's still a 1. That's what changes up. My bad. But yeah, so like whatever, you basically only, when you're doing these limits to infinity, you can basically you can basically ignore everything else that's there and only look at the coefficients of the biggest terms, in a sense, because that's what's going to dominate everything else. So I can tell you that like limit as x goes to infinity of like 30 x to like 57 plus like 4x to 12 plus 3x squared over, you know, like 10x to the 57 plus 3x 9 minus 2. I can tell you that this is going to be 3 because I can get rid of everything else. And then I just look at the coefficients of these, right? Because I'm just going to factor this all out. This is all going to go to 0. And I'm just going to be left with 30 over 10. And it's just 3, right? So pretty, not too bad. So if I sort of like revert everything here, 2 way, what's with 1? And I mean, this sort of like shows you, you know, you have your vertical asymptotes at these 2 points, right? Funnily enough, if these were actually x cubed, then this negative infinity would be different, right? Because if you plug in a negative infinity and you square that, well, that's just going to become positive. But if you do it 3 times, you multiply by itself 3 times, it's going to become negative. So that would be negative. So something to like sort of keep in mind. And I've actually like done it. I don't know if you can like see this too well. But this is like the graph for that function that we were working with. As you can see, we're going to 5 right here, right? See that? And then right here, we're going to 1 in the y. So we know that we're good. And, you know, we got that it's positive infinity from the right, negative infinity from the left. So, I mean, that's sort of cool, right?
Yeah, no, that makes a lot more sense.
Glad to hear it. Are you planning on taking the exam like tomorrow, or are you gonna like wait till like Saturday or something?
I'm not sure. I'm supposed to get my vaccine tomorrow afternoon, so I'm kind of nervous that I'm not gonna feel well, so I might just end up taking it on Friday.
Yeah, I get that. Are you taking? Is it just your first dose?
Yeah.
Okay, are you doing it through Tulane?
Yeah, I'm doing it through Tulane.
I got my first dose through Tulane 2 weeks ago, so my like second is like next week. I personally didn't really feel too bad. Right when I got home though, and I never got COVID, so that might have like been better for me. But right when I got home from my vaccine, from getting the shot, I popped 2 Tylenol like as fast as possible. And then I think that like sort of just prevented me from getting hit with anything in the future because honestly I felt fine. It was just like a little sore. So you should be all good. So
Yeah, that's what I'm hoping. I've read like different things about like what you should do about taking like pain relievers after, but like everything that I read just said it was fine. So I might actually do that just in case because I want to be able to study and get it over with before the weekend.
yeah.
So it's kind of bad timing that I did that, but I really wanted to get my vaccine.
No, I feel that one. I feel that 100%. That's good.
Yeah.
Yeah, you should be fine. I didn't really do any reading beforehand. That would have been smart. So,
Yeah, well, you should be fine.
we're hoping to be good. Okay, well, it's 8:30 now, so
Yeah.
I think here, but hopefully this was like a bit helpful, just looking into the different problems. I'm sorry I went over like related rates very in depth and was like stressing that, and then it ended up not needing to be a thing. I just remember that was like a big part of our exam, so I just like didn't really realize.
Oh, no, it's okay. That's something to know.
So,
All right. Have a good night. Thank you so much.
good one.
You too.